can see around 3 people waiting on YouTube. Once we start the streaming on YouTube, we will go ahead and continue. Okay. Can someone please confirm whether it is streaming on YouTube or not? Yes, is it? Is it streaming? Okay, fantastic. So I guess it is time for us to start the session and go ahead. Okay, great. So, guys, this is the new module. We are going to rush through the most important topics in this module, and then later, we will go into much more details and more problem solving when we meet offline, right? So, ordinary differential equations, we know that they look like dy by dx equals f of x comma y, right? And yeah, so the initial condition would be y of x naught equals y naught, right? So that would be the initial condition. We have not really gone through the initial conditions to huge detail as of now, but in these numerical solutions, we will be considering the initial condition or the boundary condition with huge importance. So, for example, uh, uh, an ordinary differential equation would look something like y. We can also have y of 0 as equal to 5, right? And what do we have to find out? We have to find out an expression. We need to find an expression for yx. We shall be using a few methods, right? One of the first methods that we're going to talk about is called the Pickard's method. Pickard's method, right? That method is again a method to solve our given uh, first order equation. But from the Pickard's method and Euler's methods are the methods that we are going to learn about in this particular session. Okay. Now, why do we need numerical solutions, right? First of all, let us appreciate the fact that an equation like dy by dx equals x is easy to solve, right? It's easy to solve. A little tricky, right? So this would be a little tricky to solve. But if we have an equation, let's say dy by dx equals x square plus xy minus y using analytic methods, it cannot be solved. Hard using analytic methods. We would be, but we are engineers, right? So engineers need numbers. Now, how do we get numbers? An explicit solution to the equation using properly. Uh, See, the polynomial is the easiest solution to any equation, right? Can we get a polynomial solution to the equation that you can using something called the numerical method? The numerical methods. So, having given this small introduction to why we will be using numerical methods, let us now start with the Pickard's method. Okay, so again, that we mentioned, these are going to use a first order differential equation. There is no issue in allowing x and y to be there on the right hand side. This method, is called after French mathematician Picard in the 19th, end of the second half of 19th, beginning of 20th century. uh, is he has got huge experience with functions. So the Pickers method goes as follows. Um, okay, so what we'll do is that let us take an example and try to solve that example. In the meantime, we'll try to understand. But of course, there is an initial condition over here which shall be used to solve this problem. So let us take a working example and try to understand the process. We'll take one working example from each process. All right. Okay. Now the problems would be in this format. Solve, let's say, a very easy equation: dy by dx equals y plus x. Right. We can solve this problem analytically as well by taking the y on the left hand side and finding out the integrating factor, right? That is one method. The second method would be to find out the symbolic form of this equation and solve it. But if we are to solve this problem using numerical methods and specifically Bicker's method, we shall require definitely an initial value. So let us say that when x is equal to 0, the y value is 1. So this is how the question is going to be posed in front of you, right? Uh, Maybe in an examination setting or an assessment setting or later sometime. Okay, on the top of the screen, right? The first thing that we do is we shall write down the solution as follows. We shall write down y equals y naught, right? Plus uh, see, a small integration has to be done, right? Integration of uh, 0 to x, right? F of x. Okay. Now, in our given problem, uh, I would like to annotate that y plus x is same as f of x comma y, right? X is x naught is same as 0 and y naught is same as 1. These are the different results or numbers that we would require here, correct? So we would uh, so the value of y also we would want to substitute in our equation here, why not? And yeah, so let us try to substitute the values of f of x plus f of x comma y and find out the integration and see what turns out, right? Okay, so y naught is equal to 1, right? Plus integration of 0 to x. F of x comma y is x plus y, right? You can see that same thing on the top of the screen, right? And mm, and then we have got dx at the end. Now, guys, the process goes as follows. Um, initially, in place of the y that you can see over here, okay, so let me repeat it. The y that you can see over here, we would substitute y equal to y naught. In the second step, this is an iterative process, right? In the second step, we would substitute y is equal to y1. And the third step, we would substitute y equal to y2 and so on, right? So we would not hesitate to write y1 over here and compute the value further. Okay, so the equation is considering y naught, right? Y naught is equal to 1. So it would be x plus y naught. In place of y naught, we'll put 1 and close the bracket here, write dx, right? Please note that we are when you see at the right hand side, there is no y left at all. So this gives us y equal to some function of x, and it makes computation easy, right? It is explicit. There is no implicit or composite function concept here. It is going to be yx equal to some function of x. Y is a some function of x. That is what we want. This is the first iteration. The first iteration. All right. The first iteration. In the first iteration, plus 1 plus x, right? And this will go from x equal to 0 to x equal to 0, right? So since the lower limit is x equal to 0, we can safely ignore that part because there are no constants here. But still, if I would want to write down the steps in a beautiful way, when you put x equal to x, we get x squared by 2 plus x. And then when you put x equal to 0, when you put x equal to 0, we would get 0 squared by 0 plus 0, right? Close the bracket. There is no doubt that the right hand side function is just consisting of x. So after the first solution, in first iteration, our solution is yx equals 1 plus x squared by 2. That is the solution after the first approximation or the first iteration. Now, we can do 2 or 3 iterations, maybe one more iteration, and then we can move on to the next method, right? Formula that we had written previously, y equals y naught plus integration of 0 to x f of x comma y plus dx, right? So now this time what we'll do is that we will this is all because we are using the same formula again and again, right? The integration that we are doing on the right hand side is, here again the integration on the right hand side, we shall be using uh, x y equal to y1 in this integration, y equal to y1. Okay, so every time you see we are taking the previous result, the iteration of the previous result, and we are substituting it in the next process. So our previously y1 is equal to 1 plus x squared by 2, right? So let's substitute the values, right? So our y1 is going to be okay. Now now let's, what we'll do is that the value of y1 would be calculated at x equal to 0, right? So we'll do that in a while, but before that let us write down the integration. Let's open up the integration. 0 to x plus x cubed by 3, x cubed by 6. I hope it is all clear with the function substitution. Okay, now we might want to move on to the next method, right? Quickly, so that we don't uh, jump over too many problems on the same topic. The next method, I would want to go ahead with the Euler's method, right? And yeah, the Euler's method. Let's see. This is a black ink. EULE, right? One is the Euler's method, and is the modified Euler's method. We will go through the modified Euler's method because that is more relevant to our uh, study of our like subject, right? So again, in the modified Euler's method, um, we basically there is a tangent, and we draw the tangent at a particular point, and based on that we do the approximation. So the core idea is as follows. Some tangent is used for the approximation. The tangent is used for the approximation. Okay. Now, again, let us consider the same equation. Uh, let's take an working example once more, right? And and maybe like given that given that y of 0 is equal to 1, right? There's an initial condition given, there is an equation given, and using these two uh, given information, we would want to solve it. Now, when it is asked to solve, right, the question would ask you also to maybe find y of 0 point, like let's say 3, right? So this could also be arguably asking you to find out a specific value of y, specific functional value. But the process is pretty similar if you want to find out y at 0.2 or 0.5. It's just that, when we do the calculation has to be done in a different way. That's it. Okay. So the method here in the Euler's process is a little different than how we had find out how we had explored in the process of finding out the solution in case of the Picard's method. Okay. Here we are going to create a table, right? We want to arrange our data in the tabular format, and once we see, I'm giving you the tabular format because it helps in arranging the data in a more uh, in an easier way. And since most of the audience here are computer science people, it will be easier for you to go ahead and write a computer program to automate the process, right? Okay. Again, uh, there are multiple automation algorithms. There are some artificial intelligence, machine learning, data science algorithms which use methods like this to solve ordinary differential equations encountered in various places, right? Not only ODEs but also PDEs, which form the basis for neural network um, architecture. Okay, let us take up uh, the solution over here, right? So there is an approximation that we have to do here. This is x equal to 0 on the number line. This is x equal to 0.3, right? So at x equal to 0, it is given that y is equal to 1. At x equal to 0.3, we have to find out what is y. This is the crux of the problem, right? At x equal to 0, the value is given. At x equal to 0.3, what is the value of y? This is the entire calculation. Now, let us find out a number which is, like small, but not very small, but also not bigger than 0.3, and very easy to calculate with. So that number can be approximated as 0.1. And usually when we solve problems, we take a particular value of a parameter called h as 0.1. Now, someone might ask, sir, why do we take 0.1? So, professor, we take 0.1. We can also take 0.01. But if we take 0.01, of course, the accuracy will be more, but a lot of steps have to be covered there, right? Now, since we are doing with pen and paper, I think 0.1 is a decent enough method to way to go, because what we'll do is that in the process of the solution, we will use this x equals 0 value, I mean y equal to 1 value, to find out the value of y at x equals 0.1, right? This is the first step. Then using this value of y, we to finally find out the value of y at 0.3. Right? So again, it's a number line thing from 0.0 to 0.1 to 0.2 to 0.3. So we'll be using three-step method, right? If you look at the top left corner, there is a number line, there is 0 to find out 0.3. It's an incremental process. If it is 0.4, we'll use 0.1, 0.2, 0.3, 0.4, right? Of course, you can also do, I mean, uh, let us, like be lenient in understanding this process, right? We can also have a number line written in this format. We can have 0.0. The number of steps has got an effect on the solution, but the theory of the solution remains the same. Also, not only that, you can even have you can reach from 0.0 to 0.3 in 30 steps, 0.02 and so on, all the way. The last step would go to 0.3 from 0.29. So there will be 30 steps here. That is also fine. Now, for every process of numerical solution, there is some error. We will not get the exact solution, right? It is always an approximate solution. So, based on how much error you can tolerate, we shall be using the value of h, right? So, let us assume that in our case, we take h as equal to 0.1. Okay. Now, when we take the value of x as 0.1, okay, so now, let us try to draw a table, format the data in a tabular format. So the first column would be, let's say, x. The second column would be the value of y dash. The value of y dash is x plus y, right? Because the equal variable name. Okay. Then there is something called a mean slope, right? Mean slope, which is the average of some of the slopes that we'll be considering, and um, like there is a formula we are going to write over here. The formula is going to be the old y, plus I mean we are writing the new y over here, right? So it is going to be the old y plus h times the mean slope. Okay, the mean slope. So we will calculate the value of the mean slope, multiply that by h, and add it to the old y, and that will give us in a more structured way. Um, if you are writing a program on this one, you can use temporary variables for each of these, declare local variables for each of that last local variable y. You can take it outside the loop. Okay. Now the first value of x is 0.0, right? When x is equal to 0.0 and y is equal to 1, because given that equal to 1, then the value of y dash will be 0 plus 1, which is equal to 1, right? This is the slope. This is the slope here, right? So yeah, when x is equal to 0, the slope is equal to 1, and the mean slope, we don't calculate that anyway, but write equal to 1 over here, right? The old y is equal to 1 because y is y, right? So this would give us 1.1. Okay. Now this is done with x equals 0. The case is over here, right? Okay. Now what we'll do is that here, let us take x equal to 0.1. When x equal to 0.1, see the slope y dash is equal to x plus y, right? So x plus y would give us, so yeah, I think mean slope, right? The pink lines are showing the mean slope calculation, and we are considering the value of x and y for calculating the current slope, right? And then now we will look at how to find out the value of y, right? Now the value of y has to be, again, since we are looking at x equal to 0.1, y we have to write plus h is 0.1, right, multiplied by the mean slope, right? Now the mean slope that we have got in the third column is 1.1 over here. So 0.1 multiplied by 1.1, right? And that would give what is the value here? I think it's 1. And that would give us 1.11. Right? So this is the new value of y that we have obtained. I mean methods for all intervals, right? Okay. Now once we have got this for 2, we'll go for x equal to 0.2. So 0.2 again, right? The next column is basically we need to find out the value of the slope, right? So the value of the slope is correct. So we have got 0.2 plus the value of y, the old value of the previous value of y is 1.11, correct? And this would give us 1.31, right? This would give us 1.31. Mean slope is, again, let me use, let's say the sky blue color, and I'll draw a box over here, right? And I'll draw another box over here. So we'll take the average of 1 in the following way, right? It's pretty straightforward. So it would be half times 1.2 plus here 1.255, right? So that is going to be our new slope, right? This y value. The old y value is 1.11, right? So the whole valuation at each level. If we do multiple iterations at each level, the answer will be different. Okay. So this plus h is 0.1 in light green line. So this would be written as 1.255, 1.2355. Now this is our new value of y for x equal to 0.3, 0.3. Right? First of all, we'll find out the slope, then we'll find out the mean slope, and then we'll find out the new value of y. Mean means average, right? Average slope. So first of all, I'll again use orange circle here. First says y, right? From here, from here to here, all the way to here. So this value is going to go as 1.5355. Now we have update says that we have to take the half of the sum of the previous slope and the current slope. So let me consider this red ink, right? And I'll draw a small cloud over 1.31 in the 0.2 column in the row, in that row, and I'll draw a 31 plus 1.5355, correct? So we'll get 2.8455, 1.42275. I hope I'm after it, right? Yes, sir. Let us now uh, say what is our y at 0.3. So y at 0.3 is equal to 1 multiplied by the previous mean, the mean slope, the previous slope and the slope before that is one column in the same row, right? 1.42775. And therefore, the solution is going to be as follows. Y at 0.2 is equal to, by observing that the y value is given over here, I'll draw a small box there and I'll bring it here, right? A small box like structure. Calculator, it says that it is plus 0.142775. 37, 38, right? 38, oops, 38, 732, 3732, 37325. Using the modified Euler's method, 7325. So this is how we find out the explicit value of a particular function, the solution of the differential equation. Yeah. I guess we will stop here for